Okay, so today we are going to discuss the physical mineralogy and the important mineral groups. So firstly, I will just touch upon some basics. So if when we are starting with physical mineralogy, the most important thing is to know what a mineral is basically and some important points related to it. So just note the important points down, whichever you find important. Okay. So firstly, what are minerals? Okay, minerals. There are a few important points as far as minerals are concerned. A mineral is a solid crystalline structure or a chemical compound. I will write point wise. Anything that satisfies these 5 points is considered to be a mineral. Okay. So firstly, it should be solid. Secondly, there are exceptions as well. I will mention it here. Secondly, it should be crystalline. Okay. Crystalline means it should have a crystal structure, a defined crystal structure. Thirdly, it should have a well-defined chemical composition. Well-defined chemical composition. It should be formed by, it should have been formed by inorganic or geological processes. Inorganic, or we can say geological. Just a second, let me. Yes, yes. Or geological processes. Okay. It should not be formed by organic processes. All right. So any anything that is formed by organic processes or anthropogenic processes or man-made processes and also justifies all the other points, then it is not considered to be a mineral. So a mineral must always be formed by inorganic or geological processes. Then we have the last point, that it should be a chemical compound. Okay, though third point also fulfills it, but still I'm mentioning it here. So whatever substance or whatever thing that justifies these 5 points is termed to be a mineral. Okay, we will go through some important facts, such as, let me mention it over here. First one being synthetic diamond. You know, just a second. Synthetic diamond and rubies are not considered as minerals. Okay? Not minerals. Why? Because they are formed, they are, or rather we can say, they are not formed by natural processes. Not formed by natural processes. Okay? Ice, is ice a mineral or is it not a mineral? What is an ice? Is it a mineral? Anyone?
Yes, sir.
Yeah, right. So basically, ice is a mineral, but just a second, someone is joining. So basically, ice is a mineral, but its liquid phase, that is water, is not a mineral because it has a liquid phase. All right, ice is a mineral since it justifies all the points that we have discussed above, all the 5 points to be a mineral. So it is a mineral since it is solid. Okay, in phase, it has a crystalline structure. Ice. Which crystalline structure does it possess? Does anyone know? What crystalline structure does ice have?
Hexagonal.
Yes, right. Hexagonal. So ice has a defined crystalline structure. It is solid. It has a well-defined chemical composition. Okay, H2O in solid phase. It is formed by an organic process. All right, by cooling down liquid, and it is also a chemical compound. So ice is a mineral, but its liquid phase is not a mineral as liquid doesn't have any crystalline structure. Also, the phase is liquid. So these 2 points rule out its liquid phase to be considered as a mineral. Okay. Then we have refined sugar. You may have these options or questions based on these. Refined sugar is basically crystalline, but it is not a mineral because it is again man-made. Okay, it is crystalline, but not a mineral. Alright, it is crystalline but not a mineral because it is man-made. I will write it here because it is man-made. Then again, glass is basically made up of quartz, right? Glass made of quartz. I mean, the glass that is made of quartz, basically made of quartz. Is it a mineral or it's not a mineral?
Not a mineral.
Yes, it's not a mineral. Why? Anyone? The reason why it's not a mineral?
Because it have not any uh, internal atomic
Yes,
structure.
yes, yes. It doesn't have any crystalline structure. Alright? Doesn't have any crystalline structure. Or I can say crystal structure. There is no internal arrangement of atoms to have a crystalline structure. We also have rust. Rust. Rust again not a mineral. You can sometimes also expect assertion reason based on this. So you need to know the reasons why they are mineral or why they are not mineral. Okay. So the reasons get important. Rust is not a mineral, although it has its composition very similar to goethite, right? But why rust is not a mineral? Anyone?
So it does not have a particular shape and size.
Yes. Basically, it cannot be considered as a solid, right?
Yes, sir.
Yes. So it cannot be considered as a solid. So even though it has its composition very same as goethite, I will write here same composition as goethite. Okay. Still, it's not a mineral. No shape, no defined shape. Actually, I should write no well-defined shape. These annotated slides also I will upload. No defined shape. Okay, but there is an exception here, that is mercury. Mercury or mercury, whatever you pronounce it as, mercury. It is considered a mineral even though it is a liquid. Considered a mineral, mercury, even though it is liquid at normal temperature. Okay, so there is nothing as specific as any reason for it in text or wherever you find it. It's just mentioned that for historical reasons it is considered to be a mineral since ages, even though it is liquid at room temperature. Okay, liquid. Just a second. No, it is not working. Yes. Liquid at room temperature. So these are like some of the basic points for minerals. Alright. So which kind of mineral do we have as most abundant ones? Like silicate or non-silicate?
Silicate.
Yes, everyone must be knowing this. Silicate minerals are very common. Okay. Just 1 second. Okay. So basically, for a fact, we know that plagioclase is the most abundant mineral in Earth's crust, right? Most abundant mineral in Earth's crust. Other silicates are abundant too. In contrast, we have non-silicates that make up less than 10% of the crust. Non-silicates actually less than 10% of the crust. That means more than 90% are silicate minerals that form the crust. Okay, but have you ever thought why is this? Why is it so? We will discuss the reasons here, but before that, let's see first how the percentages are. Okay, so this is in terms of volume percentage for common minerals. Okay, in Earth's crust, I'll write it here, volume percentage of minerals in Earth's crust. So we have somewhat such kind of a distribution, and you can easily find this diagram. It is approximately 39%. Easily find this diagram in text like textbooks like Dexter Perkins, William Denise. Okay, this volume percentage variation. Plagioclase. This is plagioclase. Basically, plagioclase feldspars are the most abundant, followed by what is the second most abundant in Earth's crust? Second most abundant, we have two actually, 12%, and another category is also 12%. So these are almost similar. Okay, that is K feldspars and quartz. K feldspars and quartz. These are approximately equal to 12% each. Alright. Then we have around 11% of pyroxenes. Around 11%. That is just a little less than quartz and K feldspars of pyroxenes. I will write PYX for pyroxenes. It includes orthopyroxene and clinopyroxene both. Then we have around 5% of amphiboles. 5% of amphiboles. Okay. If you wish, you can note this down so that you can have an idea of increasing or decreasing order. Okay, so many a times the question also comes up in terms of order, arrange in terms of order of increasing or decreasing order of mineral occurrence. Okay, then we have around 5% micas as well, 5% clays, and then 3% other silicates. So we can have similarly 5% micas, around 5% clays here. So this has been left too much of space, but it is less than 3% other silicates. Okay, so I'm not mentioning these down. This is 5% again for micas here. This is 5% again for clays, and this is 3%. There are all the other silicates constitute to 3% apart from these that we have mentioned. So basically, coming back to the question, why non-silicate minerals make up less than 10% of the crust, and why 90% of the crust constitutes of silicate minerals? So basically, the important fact is there are 13 elements, 13 elements, 13 elements that make up nearly 99.5%, 0.5 weight percent, I should write 5 weight percent of the crust. Okay, so all the common minerals that are expected to be made from these elements itself. What are these elements? I will write it here: oxygen, silicon, aluminium, iron, we have calcium, sodium, potassium, magnesium, we have titanium, hydrogen, phosphorus, manganese, barium. I guess 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So these 13 elements make up nearly 99.5 weight percent of the crust. And the common minerals are expected to be made from these. Oxygen and silicon are the most abundant elements out of these. Okay, oxygen and silicon are the most abundant in the Earth's crust. So these naturally lead to an abundance of silicate minerals. This is one of the reasons. Since oxygen and silicon are the most abundant ones, so oxygen and silicon combine to form silicate minerals, right? So this fact that these are the most abundant ones, this fact naturally leads to an abundance of silicate minerals. So like it is no wonder that other types of minerals or minerals that include rarer elements as key components are less common. But there is one more reason, that is high polarizing ability of silicon. Silicon can easily be polarized, can easily be combined to other elements to form compounds, chemical compounds. So I will write it here: high polarizing ability. So this is one of the most important reasons why silicate minerals are so abundant. High polarizing ability of silicon or silicon, whatever you say. Okay. So everything clear up to now? I guess everything must be clear up to now.
Yes, sir.
Okay, all right. Then we will have a look at some important silicate mineral subclasses. Okay, let's have a look at them. Some important silicate mineral subclasses. Then we will go through each of those subclass one by one. Silicate mineral subclasses I will write. So here we will have a table. Alright, subclass. Then we have SI is to O ratio, which is again an important point. SI radical, like what kind of general formula does the SI radical point have. We also will include the examples of those subclasses. Again, like for a few, we will include mineral formula. Okay, for the common ones. So the first one we have, let's begin with framework silicates. Framework. Okay. So here I will write silicates so that I don't have to mention silicates again and again. Silicates. So basically framework silicates, it is also known as ectosilicates. Ectosilicates. Okay. What SI is to O ratio that we have? 1:2, right? The SI radical that we can write here is SiO2, or in terms of generalized form we write AlX Si 1 minus X, okay, O2. So if X is 0, what do we have? Al0, that means Al is not there, SiO2, right? If X is 1, we have AlO2, Si will become 0. Okay. So the examples we can write here as quartz, albite. These are the examples here. Mineral formula, if you want, I can write SiO2. For albite we have Na, Al, Si3O8. So what is the other end member for albite? Like, if you know.
Anorthite.
Yes, anorthite. So the other end member has Si2O8, right? But albite has Si3O8.
No, sir. NaAl2 Si2O8.
Si3O8 is there for albite. What is the mineral formula for anorthite, if you know?
CaL2Si2O8.
Yes, so that is what I was telling, CaL2Si2O8. So for anorthite we have Si2O8, but for albite we have Si3O8. So remember this point. It is just because of substitution. In place of one Si, here we have one more extra Al in anorthite. Here we have only one Al. Okay, so it is nothing but somewhat derived from this SI radical formula. Alright, and also to have a balanced output. Yes.
Can we say that maximum substitution takes place in anorthite then according to this formula?
Yes, we can say that. Like in terms of albite and anorthite solid solution, we can say that the maximum substitution takes place in anorthite, and it decreases as you move towards albite. Okay.
Okay.
Yeah, substitution decreases because you can also see here Ni has +1 charge, Ca has plus 2. So to balance it out, here Si has plus 4, Al has plus 3. To balance these things out, we need to have one more Al if we need to accommodate Ca in place of Na. And if we need to accommodate Na, we need to have Si in place of Al. Okay, so only one Al can take place here. You can balance it out, the charge. Like for O it is minus 2, so O8, that means it is minus 16. Okay, so now accordingly you can balance it out for all the cations. These all are cations, O is anion, and same goes with this formula. CaAl2Si2O8. CaAl and Si are cations, O is anion. So just balance out the formula. Here again it is minus 16. So to have plus 16, we need one more Al here and one less Si. And to have plus 16 in this case, because here Na is present instead of Ca, so we have one less Al and one more Si. Okay. So I hope this point is clear. This is not that typical, but still I just mentioned it because this is a vital difference between albite and anorthite chemical formula. Then we have sheet silicates. Just write sheet here. Sheet silicates. It is also known as phyllosilicates. EHYLLO. Phyllosilicates. Okay, put a dash. Now, what do we have as Si/O ratio here?
2:5.
Yes, it is 2:5, and also it is equivalent to 4:10. So many a times you will have chemical formula as 4:10. Okay. So 4:10 is nothing but, when it is simplified, it is 2:5. So the side radical here that we have is Si4O10, and the charge is 4 minus. Okay. Here we have, for example, we can write pyrophyllite. Pyrophyllite is one of the examples, and its chemical formula is Al2 Si4 O10 OH twice. So it is nothing but a hydrated compound. Do you know the difference between hydrated compound and like the difference between products that is formed, one by hydration, second by hydrolysis? You know the difference? Hydration adds OH minus ions, and hydrolysis adds H2O compounds as it is. In many formula you must have seen, here there might be a chemical compound dot H2O, right? So that is a product of hydrolysis. And if you have OH minus ions, it's a product of hydration. These two are different processes. So in hydration we have often H plus ions are expelled from the solution, but in hydrolysis that is not the case. H plus ion is there in the compound here. Okay, so this is the difference. So just bear these things in mind. These are just simple things. Then we have single chain. Just a second, someone is joining. Okay. So then we have single chain silicates. Single chain are also known as ionosilicates, right? Single chain ionosilicates. It has Si/O ratio as 1:3, or equivalent we can say 2:6. Alright, in many chemical formula and many compounds you will find 2:6 ratio. 1:3 is the simplified version of it. So that is SiO3 2 minus, or if it is 2:6 ratio, Si2O6, here we will have 4 minus. Okay, so the most common example is enstatite. and we can write it as its chemical formula as Mg2Si2O6, or also at many places you can find it as Mg2, which is same eventually, SiO3 twice. So it is same basically, no difference. Then we have the fourth one, double chain. Sorry, double chain. Single chain inosilicates are like, which kind of mineral group is the prominent example? What is an anstatite?
Ferrocylate.
No, like I am asking in which mineral group can you place anstatite? Which mineral group does anstatite belong to? Amphibole, pyroxene, mica.
Pyroxene.
Pyroxene.
Yes, pyroxene. And in double chain we have amphiboles, right?
Yes, sir.
Yes. So here we have Si/O ratio as 4:11, or the complex form is actually 8:22. Okay. So the radical becomes Si8O22. The charge is 12 minus. We will discuss this about the charges and all. And the most prominent example that I can write here is tremolite. There are many more examples for each category, but I am just writing one common example. Ca2Mg5 you have Si8O22. Again, amphibole is a hydrated product, so OH twice. Okay. Then we have ring silicates. Ring silicates are also known as cyclosilicates. Ring, I will write ring silicates. These are also known as cyclosilicates. It has cyclic structure somewhat. Okay. So the Si/O ratio is here again 1:3, or it is 6:18. In many formulae you will get 6:18, and its radical also forms. So most of the times the SiO radical has the complex structure in it, that is Si6O18, and it will have 12 minus. So this 12 minus, 12 minus here, 4 minus, 2 minus, 4 minus, all these are the balancing figure that is remaining after having this complex terms inside. Okay. So you can just balance it out for anion and cation, the charges, and the balancing charge that you get is this one, 12 minus. So that means this 12 minus means this will form a compound with the cations only if all the cations have plus 12 charge in total. Okay. So this is the basic thing that we see, but after that we see which kind of cations can go through these anions, which kind of cations can actually form compounds. So again we see the chemical structure, if the structure is possible or not. It's not like plus 12 is needed, then whatever cation we will place here. No, it won't form a compound always. Then the chemical structure comes into place, if the structure is possible or not. Okay. So we have common example as tourmaline. Tourmaline is a pyroelectric or a piezoelectric. Does anyone know? Like while solving questions, you must have got this for sure.
Piezoelectric.
Actually, tourmaline is both. Okay, so always remember this point. Tourmaline is piezoelectric and also pyroelectric. So remember this point. Tourmaline is an example of both, piezo and pyro both. Okay. So tourmaline has a very complex formula. You don't need to remember this though, but if you remember it, it's well and good for you only. But if you don't, it's not that big an issue. Okay. Sometimes in such kind of exams like CUET, BHU, there are questions on chemical formulae. So for these exams, it will be helpful if you remember. So Only sometimes they put out questions on chemical formula directly, though they should not form questions on of such type. I don't believe in this thing because it is not testing anything out of you, it is just testing that who has memorized more. So it won't differentiate you skill wise, right? If you are memorizing such big formulae, so like I don't think anyone is gaining anything out of it because at such times everyone has a mobile phone. If it is required at any point in time, you can just simply Google it and you will get the chemical formula. So the rote learning questions I haven't like liked them anyways. I don't know why they still keep on having questions based on rote learning pure. Yeah, some factual questions are always welcome, but pure rote learning questions make no sense in today's time. But still, we can't help it. If they ask it, it's for all. Everyone has to answer. Questions are same for everyone. Then we have isolated tetrahedra. Uh, Isolated tetrahedra are also known as mesosilicates, right? Mesosilicates. It has 1:4. It is isolated. It isn't pairing up with anything. So simply 1:4 is there for isolated tetrahedra. Here we have SiO4, 4 minus, first right, and a member of olivine group. This is one of the examples. First right. Okay. First right to phyolite. There is that complete olivine group. Mg and Fe end members. Mg2SiO4. The Fe end member is a phyolite. Alright. Then we have the last one, the last common one, that is paired tetrahedra, paired tetrahedral silicates, paired one, also known as sorosilicates. It has 2:7 Si:2O ratio, 2:7, and its radical is Si2O7 6 minus. So again, many examples are there. One common one is acarbonite. Okay, it is Ca2 Mg Si2O7. Like I was mentioning here, like you need to have 6 minus, then you need to have the cations plus 6. You can easily get it from here. Ca2Mg in total forms plus 6, right? Ca2 becomes plus 4, Mg has plus 2, so plus 6. Likewise, we have these charges balancing out figures. Okay, so yeah, this is it as far as silicate mineral subclasses are concerned. Then we will focus on uh, more classification of silicates. Okay, we will look at them one by one. Just a second, start it from the page only. So basically, when silicates were classified, it were classified depending upon the degree of polymerization, okay, of the SiO4 tetrahedral units. Like I will write it here. Just a second, I will write it above only, where we discussed silicate mineral subclasses. Yes. So this classification depends on degree of polymerization. Polymerization of SiO4. Tetrahedral units. Okay. So all the silicate structures that you see here, these have one Si atom at least, right, lying between four oxygen atoms. Okay. Now for a fact, I will just write it here. In this SiO4 structure, here we have O. It is a 3D structure, okay? O. Then this will go beyond the paper like this, O. Then again above the paper or outside of the paper, O. So it's a 3D structure. We are trying to understand it in 2D. Okay, so distance between, here you can see, I will write it separately here only. Distance between, we will write centers of any two adjacent O2 minus atoms is 2.7 angstrom. Angstrom, like this. So what is angstrom equivalent to in meters? One angstrom is 10 to the power, anyone?
Minus 10.
Yes, 10 to the power minus 10 meters. Okay. So this arrangement is basically universal, that in any SiO4 tetrahedra, you will find distance between centers of any two adjacent O2 minus atoms as 2.7 angstrom. But when it is polymerized, when it is forming different kind of structures, there are pressures on O atoms to complete the structure, to have a stable structure. So this distance may vary then. Okay. But in a single SiO4 tetrahedra structure, this 2.7 angstrom is the universal one. So again, you will see here, for, I will just mention a few more names for like Niso. Yeah, Niso silicates are also known as orthosilicates, right? So that you don't get confused if any other name is occurring in exam. These are isolated, also known as independent.
Single island silicate.
Yeah, it is also known as island silicates, right? So these are some of the few names for this, okay? Because it is characterized by a single SiO4 tetrahedron. Okay, so as I mentioned, the examples are here. Some more examples, you can see text for it also. For Niso, as I can say, there are examples like garnet, zircon. We have Al2SiO5 polymorphs, that is kyanite, andalusite, sillimanite. We have staurolite, we have topaz. So there are many examples. Okay. For sorosilicates, it is linked by sharing of only one oxygen atom. Okay. For soro, it will have a structure like this. Only this, like this one oxygen atom will be shared both ways. So it will have somewhat this kind of a structure. O, here it will be O, there again here it will be O. So here you can see one oxygen atom is shared, right? That is why we see 3, 3, 6 and 1, 7. 7 oxygen atoms and 2 silicon atoms. So Si2O7 it becomes, right? So in terms of sorosilicate, we call it paired, and as I have already mentioned your example, more you can see. There are many like melilite, pumpelite, so you can see them. In metamorphic species, you must have studied prehnite, pumpelite. Pumpelite belongs to sorosilicate. Then One by one we will see here some. We are just going for the structures here. Then we have cyclosilicates, okay, ring silicates. So these are ring silicates basically. How many oxygen atoms are shared here between neighboring tetrahedra?
3.
In ring silicates, you guess it's 3.
Yes,
Sorry,
yes.
it's 2. 2.
Yes, actually 2 oxygen atoms are shared in
Sir,
cyclosilicates. Yeah. Yes?
sir, sharing oxygen atom, you asking sharing oxygen atom?
Yes, sharing oxygen atom. Like how many oxygen atoms are shared in one tetrahedra? Like in one.
Yes.
Here we can see one oxygen is shared, right? In sorosilicate. One oxygen is shared with other. Like this SiO4 is also having this oxygen. This SiO4 is also having this oxygen. This particular oxygen is shared between two tetrahedra. Between this and between this. So in cyclo, actually there are 2 oxygen atoms that are shared. Okay? In cyclosilicates or in ring silicates. I will try to form a figure here. You will see like this. Si. So this is just that you understand it nicely, like how many oxygen atoms are shared, because many a times questions also come on this, and these days they have started forming such kind of questions, bridging oxygen and non-bridging oxygen, and ratios. Okay, so bridging oxygen is nothing but shared oxygen. Okay, in one particular SiO4, bridging oxygen is the number of shared oxygens, and non-bridging oxygen is the number of non-shared oxygens. So whenever you get questions on ratio of this, that BO to, I can write here NBO, non-bridging oxygens. So always have the structure in mind. Okay, that is when the structures uh, come into place, and it gets very important that you know how many oxygens are shared, how many oxygens are not shared in particular structures. So these kind of questions are like, now they have been asking such kind of questions quite regularly. So they are playing around this, but if you know the concepts, if you know the basics, even if they play around this bridging and non-bridging, you will be able to answer each such kind of a question. Okay, so for here we can see like for cyclosilicates we have, okay, so 2 oxygens are shared. Suppose first one would be this one, Si, again here would be 3O, alright, and suppose the another one that is shared is this one, suppose this below one, Si, again here will be 3 O's.
Sir, non-bridging ratio.
No, this is bridging. This is bridging means total shared oxygens. So in cyclo, this is I am drawing for cyclosilicates, for ring silicates. For ring silicates, you have 2 oxygens that are shared. So the first one is, for suppose this one, any kind of structure can be possible. For this, any kind of is possible. And the second one is this one, for example. Okay. So 2 oxygens are shared in cyclosilicates. But theoretically, what happens is infinite number of rings are possible. There can be infinite number of rings. You can go this way, you can go this way. There can be many rings that are possible. So, like I mentioned here, let's have a look here. The radical part. Look at the radical part. It is having Si6O18, right? So if on this we start putting up here beside the bracket as 2, 3, 4. So that means the rings are getting increased in numbers. Are you getting my point? So theoretically, infinite number of rings are possible basically. For Si6O18, you need to have 6 Si's. Here, what we can see is 3 Si is there, right? And calculate the number of oxygens. 3 for this, 4, 5, 6, 7, 8, 9, 10. So you're getting this?
sir.
So the structures actually vary, okay, in terms of what kind of mineral you are getting. For beryl, like for example, if I talk about beryl, we have Be3Al2Si6O18. So for beryl, again we have Si6, right? So here, if we are saying that only two oxygens are shared, this we are talking about one particular unit. This is one unit. We can have many units combined to form a particular mineral. So that is why theoretically there are infinite number of rings that are possible. Okay, so you can extend this like this. This is one unit which represents, in simple forms we have 1:3 ratio in terms of cyclosilicate that we have seen here, like this. So we can have many examples depending upon the formula. Here also we have Si6O18. For beryl also we have Si6O18. Okay, there are many more examples like exenite, bentonite, cordierite is also there. Okay, so you can go through more examples, as many examples as you want. So one simplified thing for ring silicate we can also write as, can mention it here. If you need more simplified term, we can write it as SIN, because it is always true for this, O3N, and then the charge will be 2N minus. So this is the more simplified radical. Okay, so you can just keep N as any value, 1, 2, 3, then you will have the perfect compound for a cyclosilicate structure. So as you can see here, suppose if it is 6, N is 6, then Si6O, 6 into 3, 18, charge will be 2 into 6, 12 minus. Okay, likewise. So you can have any likewise. So this is just the most simplified term for it. There is one fact for cyclosilicates. If you know this, then you can cut out many things to remember for the rote learning stuff. All the cyclosilicates, all the ring silicates are part of, or all the members belong to, hexagonal system. Hexagonal crystal system. Okay. So whichever member is a part of ring silicate or cyclosilicate, it also belongs to hexagonal crystal system. So suppose if you know that tourmaline is part of cyclosilicate, and if you don't remember that it is hexagonal, so directly derive it from this fact, that if it is a cyclosilicate, it is necessarily going to be a hexagonal system part. Okay, so this is the fact for it. Again we have then suppose inosilicate, single chain. So how many oxygens are shared here? Inosilicate,
2
no,
single chain में 2, double chain both I think 2 or 3.
actually 2.5 oxygens are shared in single chain. Okay, each tetrahedron is linked to its neighbor by sharing two oxygen atoms to form single open chain. This you must have read. It is parallel to C axis. But what happens is 2.5 oxygen atoms are shared in general, that we say. Okay, so in, like, you must have studied in double chain that we have two oxygen atoms are shared and also three oxygen atoms are shared, 2 or 3 in double chain. But what happens is two oxygen atoms are shared, half are taken from there, three oxygen atoms are shared, half are taken from there. So it comes to be 2.5. Okay, must have created some confusion. I will write it here. For inosilicate, single chain, and for inosilicate, double chain. Many a times these two get confusing because these are forming from one kind of silicate subclass. In inosilicate single chain, you have two oxygen atoms that are shared. The 2.5 I was talking about amphibole. Sorry if I got you wrong at that place. And in double chain silicates, we actually have two oxygen atoms and three oxygen atoms, but these two have half-half contribution in the overall structure. So what happens is its half contribution will make it 1 and its half contribution will make it 1.5. So that way we have in overall terms as 2.5 oxygen atoms as shared in a single unit. Okay. Here. And for inosilicate single chain, that is pyroxenes, we can say that it has two oxygen atoms as shared with its neighbors. So these are always shared parallel to C axis. This is we will like elaborate it further. We will come to pyroxene group. But for now, these are facts, so you can write these. And most of them have prismatic habit. So I'm just connecting the dots so that you have lesser things for rote learning. Okay. Though this prismatic habit may also have some exceptions, but most of them have prismatic habit. But in cyclosilicates, there are no exceptions. All the cyclosilicates belong to hexagonal crystal system. So here I have mentioned above as well for radical, but I will again mention it here in simpler terms. Si2O6, in terms of N, you can write it as N4 minus. Okay, so this N is nothing but the chains will keep on increasing if you keep on increasing the value of N. Okay, so there are examples, many examples, like the pyroxenes are there, and statite is a part of it. The pyroxenoids are there. So all the minerals belonging to pyroxene group belong to single chain silicate. Okay, so for here in double chain, there are also some very common habits, and that are like fibrous. Prismatic is also there here. Prismatic, also acicular. Acicular is nothing but needle-like structure. Okay, which has acicular structure? Any common example that you know?
Naturalite.
Yes, natrolite is one of them. Out of sillimanite, kyanite, and andalusite, which has acicular?
Sillimanite.
Yes, sillimanite has acicular, kyanite has bladed. Okay, so like remember this because many a times people get confused that which one has acicular and which one has bladed. So always remember this: kyanite is a blue bladed crystal, and sillimanite is an acicular crystal structure. Sillimanite has acicular kind of structure, like it is a needle-like, but kyanite is not needle-like; it is simply bladed kind of a structure. So for double chain, we have amphiboles. The amphibole group is there. It has alternate tetrahedra, okay, in two parallel single chains. So these are cross-linked, like I can draw it here for both these. So structures are important. You need to imagine them. While drawing it in 2D, it sometimes gets confusing. So again, it will have here. So likewise, this is the single chain. You can start creating the chains. It doesn't matter how long the chain gets. It will just add up to the value this N. Okay, if the chain expands. Then we have for double chain, it will, for like this double chain silicate, it will just simply come over here. Okay. Oh, so for such case, what do we have? This 3 oxygen atoms mostly go to the top side, and this oxygen comes towards downside. So you can imagine for double chain, without this part, just a second. So up to here, this is the structure of single chain. Okay, this is 1 unit structure of single chain. Now if we talk about double chain, let me erase it here only. Okay, if we talk about double chain, here just imagine that O's are there. Okay, here it will be Si, again 3 oxygen atoms, again Si linked to this oxygen, and then again 3 oxygen atoms. So this unit, it will expand this way. Okay, the chain will expand in such a way, and it will keep on expanding. So this complete unit forms the unit for double chain silicates. Okay, are you getting the structure point now? How the structures are forming? Are you getting it?
Yes, sir.
Okay. Actually here what I have drawn is basically you can have this as shared, like there will be one oxygen. Okay, like this oxygen is here, you can draw here oxygen. This chain will be formed like this. So for this tetrahedra also we have this same oxygen, for this tetrahedra also we have this same oxygen. Similarly here, so as you can see in double chain, what are you seeing? This oxygen is shared 1, this oxygen is shared 2, and this is half shared, right? That is why sometimes we mention it as 2 oxygen shared and 3 oxygen shared. Both kind of structures have half contribution. Here in this tetrahedra you have half contribution, here you have half contribution. Same goes with this. Same goes with this. So like I mentioned here, this derivation comes out in overall terms, in total terms, what we have is 2.5 O2 minus atoms are shared. Okay, so this is the structure. Structures get important in many ways. You need to know. So this okay, again we still have a couple of them left, like sheet silicates and phyllosilicates. For phyllosilicates, sheet or phyllo basically, they are 1. So for phyllosilicates, how many oxygen atoms are shared per tetrahedron?
3.
3.
Yes, 3 are shared. So basically, by shared, what I mean is bridging oxygen is 3, and non-bridging oxygen is, what will be the value of non-bridging oxygen?
5.
1.
Sorry.
Yes, we are talking about per tetrahedra, only one tetrahedra at a time. Whenever we talk about shared oxygen, non-shared oxygen, bridging oxygen, non-bridging oxygen, we are always talking about one particular tetrahedra. Okay, one unit. So for one unit, always there will be SiO4, right? So out of those O4, 3 are shared, 1 is non-shared. So bridging oxygen is 3, non-bridging oxygen is 1. The ratio for bridging oxygen to non-bridging oxygen for phyllosilicates will be 3:1. Or vice versa, the ratio of non-bridging oxygen to bridging oxygen will be 1:3. Okay, so many times questions come from this. You can create separate notes for this, like bridging oxygen, non-bridging oxygen, for each of this subclass. Alright, three oxygen of each tetrahedron are shared here with adjacent tetrahedra to form the extended sheets, and this is done along c-axis again here, along c-axis. There it was parallel to c-axis, right? Here we have seen in inosilicates it was parallel to c-axis. Parallel to c-axis means what I showed here, this one was c-axis, so it is going parallel to c-axis. Okay, so here we have 2:5 and sheet or phyllosilicates. 4:10 is a general one. I can write here, you can write here, just you can add n to any of these bracket terms. Sorry, you can add n to any of these bracket terms. If the chains are getting extended, this n value will get keeping higher, will be getting higher and higher. All right. So in phyllosilicates, there is a fact I will write here. It is an important one. So mention this down if you don't have or if you don't know this. For phyllosilicates, write phyllo or sheet. For phyllosilicates, what happens is if there are Mg and Fe ions, Mg and Fe ions are present, then it is known as brucite sheet. Brucite sheet. So phyllosilicates have their prime example as micas, okay? And if Al ions are there instead of Mg, Fe, if you have Al ions, then it is known as gibbsite sheet. So I don't think if a question will come on this or not, but if a question will come on this, believe me, very few people will be able to answer this. So this gets as an important point. And also in terms of this shared oxygen atoms for each structure, not everyone has the basic concept of this in terms of structure. I've drawn the structures here to let you imagine them so that you can get the questions right. Okay, so not many people have the basics of this. They just remember the SI/O ratio and some examples maybe. Only this much most of them know, but only a few who are like preparing really hard, who are preparing really well for each topic, they will go into this much depth for bridging oxygen, non-bridging oxygen and all this stuff. Okay, so as mineralogy is really important, you can expect in-depth question from mineralogy anytime in any exam that you appear for, if you are an earth science aspirant. Okay, so these kind of information get important. Now here in any structure actually we can see that Al becomes an important substituting element, and in phyllo basically I was talking here, so I will write here only. Al basically becomes an important substituting element in many structures, right? But in phyllo what happens is OH, F, Cl, any of these may always be present. Okay, these I will write may be present. Alright, so sheets always form hexagonal planar network. They are confined to one particular plane. Okay, like in this plane, in the screen you are seeing, this is one particular plane. So sheets are confined to one particular plane. When it is going, like it is increasing its number of planes, like it is not being restricted to only one plane, then it forms framework silicates, tectosilicates. Okay, but if this sheet is confined to just one plane, then it belongs to phyllosilicate. So these sheets basically form in phyllosilicate hexagonal planar network. Okay. So examples are mica, chlorite. You can have such kind of examples. Then we come to last one, the tectosilicates. So how many oxygens are shared in tectosilicates?
All the oxygen.
All
Four.
4. Yes. So here the bridging oxygen now becomes 4 and non-bridging oxygen becomes 0. Okay. So all 4 are shared in framework or tectosilicates.
Non-bridging is how many non-bridging is two?
Non-bridging is 0. The total number of, if you talk about shared atoms and non-shared atoms, let me write it this way. It will be I think it will be easy for you all to understand. Let me write it this way. For any silicate subclass, bridging oxygen plus non-bridging oxygen will always be equal to 4. Or for bridging oxygen, we can say it as shared O2 minus atoms. Sorry, this 2 will be above in charge. Okay, shared O2 minus atoms, and these are non-shared. So just to let out your confusion, always remember this fact. And this we are talking in terms of one tetrahedra. Always we talk in terms of one tetrahedra when we are talking about shared atoms. One tetrahedra which has SiO4 unit. SiO4 4 minus unit. So SiO4 has only 4 oxygen atoms. That is why bridging oxygen plus non-bridging oxygen will always be 4, equal to 4. So for framework tectosilicates, we have bridging oxygen as 4, so automatically non-bridging oxygen becomes 0, because all 4 atoms are shared. So the non-shared atoms comes down to 0. So I hope now you got this point. Now this must have given you a bit more clarity. So remember this thing, yeah. You won't have any doubt after this. So this is for all silicate subclasses. Okay. The framework, ino, sheet, meso, soro, or whatever. Philo, cyclo. Okay. So here 4 oxygen atoms are shared. Every SiO4 tetrahedron shares its corners with other tetrahedra. So as I said that this is a 3D structure. So that is why it is now not confined to only one plane, because it is a 3D structure, right? This oxygen is going out of the, inside the plane, and this oxygen atom is coming outside the plane. These 2 oxygen atoms are suppose not dotted lines. These 2 are in the plane only, in this particular plane. This is inside the plane, this is outside the plane. So now all 4 are shared. This will be shared to silicon here. This will be shared with another silicon here. So now it will depend on the structure, how it is getting accustomed. Okay. Again, this will be shared. So likewise, there will be way too many branchings in all directions. So that is why it is known as 3D silicates, framework silicates, tectosilicates. So these are the reasons for it. Okay. It gives a 3D network. So that is why we can also call it as 3D silicates. So I hope you got the structure point, everyone. This was important because you can expect a question on this for sure. Here also you can have SiO2 and you can provide N beneath the bracket. You can provide here N in terms of, so that you can have N number of chains. Okay. Here also if I close it, these curved brackets, then we can have N. So these are always basically low density minerals. These always have. For tectosilicates also I will write some facts. For tecto, at many places it is written as TEK. So these are same basically. For tectosilicates, the minerals always are of low densities. And density values often varies from 2 to 3. Low density since it is spread over the 3D network, and also they have low refractive index for similar reason. Okay, so these two are the facts for this. So if you associate such kind of facts with the subclass, it gets easier to know which mineral can have such kind of properties. Okay, so always try to associate the properties with the higher hierarchy. Like in the hierarchy, now inside of tectosilicates, we will go to many mineral groups and such that. So always try to associate these properties instead of direct associating it with each example. Try and find the properties that can be common for each of these examples, so that you directly associate those properties with its subclass. It will be easier to remember for you. So here we have a lot of examples like quartz, the quartz polymorphs, crystallobalite, tridymite, etc. We have feldspars, we have orthoclase, sanidine, microcline, we have feldspathoids, we have plagioclase feldspars, we have zeolites. Okay, so these are a few examples from tectosilicates. So this was like the basics that we have covered. Now, are you all willing to continue? I am willing to continue. If you all are willing to continue, we will just have a short 10-15 minutes break, and then we will begin with individual mineral groups. I hope you all are willing to continue. These were basics. Now we will start with individual mineral groups. If you wish, we can take this forward to next class. But if you wish, we can continue. Next class? Okay.
Yes.
Next class? Okay, alright. Yeah, like we have had more than 1.5 hours of class today. So okay, no issues. We will continue this in next class. I hope you all have got to learn something and you all understood the things nicely. Thank you all for attending. We will continue in next class. Yeah. If you have any queries, you can ask. Yeah. Yes, Shivangi.
Sir, recording of last time when 2019 paper was discussed has not been uploaded yet.
Yes. Actually, I am refining that recording. Just a second. Let me stop this.